Hi, it's Kate, and this is the second video for week 6 of Math 23. Now we know exactly what it means to talk about the infimum and the supremum. Now we're going to talk about the limit infimum and the limit supremum. Given any bounded sequence, when we talk about the infinite number of elements that follow the nth element, that's what we call the tail of the sequence. And this infinite set, it's an infinite number of elements that come after the capital Nth element, has a well-defined supremum and infimum. So let's talk about combining the notion of limit with the definitions of supremum and infimum. So the limit supremum and the limit infimum are written and defined as follows. First, let's look at the limit infimum. It's written like this: Lim Inf of S sub n, so that's the limit infimum of the sequence S sub n, and it's equal to the limit as n goes to infinity of the infimum of the elements in S sub n that come after the index big N. Similarly, the limit supremum is written Lim Sup S sub n, the limit supremum of the sequence S sub n, and that equals the limit as big N goes to infinity of the supremum of the set S sub n, where the elements are the elements in the sequence that come after the index big N. Now, what does this really mean? In practice, what you want to think about is, okay, what's happening to this infinite set, maybe from the 50th element onward for the rest of the sequence? What's the infimum of that set? How about from the 75th element onwards, from the 79th element onwards, from the 100th element onwards? What are the infimums of those sets? How about the 200th element onwards? The 300th element onwards? What are the infimums of those sets? And are these infimums approaching some limit? And the same thing with supremums. Looking at those sets, looking at just the 25th element onwards, the 30th, the 40th, the 50th, the 60th, and basically as you're looking at the tail but starting later and later, is the supremum of each of these sets approaching some limit? That's what you want to be asking yourself. So what's interesting is that if the limit of the sequence is defined as a real number, so if this sequence ends up converging, then it might not come as a surprise to you that the limit infimum of the sequence and the limit supremum of the sequence are equal, and they are the same as the limit of the sequence itself. That's a very big deal. And that goes backwards as well, where if you encounter a sequence where the limit infimum of the sequence and the limit supremum of the sequence are equal, then that means that the sequence itself is convergent and its limit is the same as the limit infimum and the limit supremum. So both of these are really important facts. And for a Cauchy sequence of real numbers, the limit infimum is equal to the limit supremum of the sequence, and so the sequence converges. That's a big deal to find out that Cauchy sequences are convergent sequences. Now let's talk a little bit about subsequences. Say here we have a sequence, S sub n, it looks like this. The way that we construct a subsequence from this sequence is by selecting an infinite number of terms from this parent sequence in order. So maybe my first sequence, the first term in my subsequence is this one, and then my second term is this one, and my third term might be S7, and so on and so forth. We keep them ordered, but we're not necessarily, we may be selecting every single term from our parent sequence, but we may be skipping a couple in between. So this red thing here, usually in your text as well as in other texts, they'll be given different serial numbers, and also since it's a different sequence, it'll have a different base here. I think in the textbook it's called T, but it's just important to note that each of these appear in the parent sequence. But perhaps not all of the elements in the parent sequence appear in the subsequence, and the order is preserved. Now, what's interesting is that when we know a few things about the parent sequence, we can say things about the subsequence. So if the parent sequence converges to S, then we know that any subsequence that's selected from it will also converge to S. What's interesting too is that given any sequence, we can construct from it a monotonic subsequence, either an increasing one whose limit is the limit supremum of the parent sequence, or we can construct a decreasing sequence whose limit is the limit infimum of the parent sequence, or both. And another thing to note is that if the original parent sequence is bounded, this monotonic subsequence that you can construct must converge even if the original sequence does not. That's pretty fascinating. And what's interesting is that this construction proves one of the most useful results in all of mathematics, which is the Bolzano-Weierstrass Theorem, which says that every bounded sequence has a convergent subsequence. And we will be proving that in class.